Great, folks, we're gonna go ahead and get started. This is if you wanted to be here for the Managing Emergent Contaminants session, that's here. Taylor Swift is performing next door if you want to go there. But obviously you want to be here instead. Um, our session today is chaired by my friend and colleague, Dr. Rebecca Munich. She's an associate professor of biological and agricultural engineering at the University of Arkansas, and her research integrates geospatial sciences and watershed modeling to assess land and water resource management trade-offs, particularly for water quality. I'm doing this all by memory, by the way. I'm not actually reading the screen. She has 10 plus years of experience in environmental and watershed modeling, with work influencing Midwest policymakers on nutrient load targets. Her research group focuses on quantifying phosphorus from manure and broader phosphorus modeling at our triple bottom line sites in the STEP Center and for the national phosphorus budget that we're developing. So please, a round of applause for her, and we'll go ahead and get started.
Thanks, Matt. Is this working? Can you
Yeah,
hear me? Okay, you
that's
can't
fine.
tell that it's working.
If
Okay.
you want to, you can also use this.
Okay, I'm gonna be really fast. So I think that intro was longer than the slides I have to introduce this section. So I just wanted to kind of jump right in because I want to give more time to our speakers. I know we started a little bit late. But why think about emerging contaminants in a circular bioeconomy? Well, I'm sure we've all seen some of these headlines. Kind of scary. There's a lot of kind of information out there with maybe not as much research. We're still trying to figure out, especially we're thinking about PFAS, but there are lots of other emerging contaminants, and we'll hear more about some of those. So we really need to start thinking about this because this information is already out there and it's already impacting, as we'll hear, our efforts to recover, value from waste, which is the whole point of a circular bioeconomy. So, there's impacts throughout the kind of idea of a circular bioeconomy if we have emerging contaminants, just from the perceptions of a circular bioeconomy to the actual how do we do it. So the technology side, and then maybe the use, and then the recirculation. So there's so many things, so many aspects in which you can think about how emerging contaminants fit into and disrupt a circular bioeconomy, that we really need to start thinking about how best to address this. From the STEP side, I'm going to be leading in our kind of second phase, not second year, fifth year, a convergence theme around waste valorization. And this is definitely a key concern that we've talked a lot about in STEPS about how this is impacting our efforts in this space. I put a couple of projects, Paul Westeroff and others are looking at, different ways to address PFAS, how PFAS and phosphorus recovery are kind of working in tandem or not, from a technology side. I'm also leading a proposal where we're trying to think about where to best recover, reutilize, maybe reduce, mitigate phosphorus pollution across the US and through different kinds of opportunity zones, and emerging contaminants is definitely going to be a key component of that. So I just wanted to quickly highlight that this is something that's a priority in STEPS, and that we'll be trying to work on alongside with many of you. So I'm gonna briefly just kind of say what you're gonna hear from these four speakers that we have today. We're gonna hear about the scale and the scope of the problem of emerging contaminants when thinking about the circular bioeconomy, technological advances that we have for addressing some of these contaminants, as well as the regulatory complexities across multiple emerging contaminants, and what agencies are already starting to do to address the issue. So I think that our speakers hit on a really nice kind of culmination of the different problems that really impact our ability to create a circular bioeconomy from waste when there are emerging contaminants present. So that's all I want to talk to you guys about, because I want to get to the really good stuff. And our first speaker today is Janine Burke-Wells. She's the executive director of the Northeast Biosolids and Residuals Association, as heard, NEBRA. And she's worked as a public servant for over 3 decades, so 10 years with the US EPA and over 20 years in local government, where she managed several wastewater systems in Rhode Island. So welcome, Janine.
Thank you.
If you want, do you want to use this mic, or do you want to walk around?
I'll be here.
Okay, stick. Okay.
All right. Can everyone hear me? Yeah, you're right. It's kind of
You can't tell.
no feedback from here. All right. So is this how we? Yep. All right. So my role today was to kind of set the table for some discussions, hopefully really productive discussions in the panel session later. But again, we're talking about emerging contaminants. Mostly you'll hear about PFAS. That's like the hot topic right now, but it's certainly the most prominent see in the news. But we have microplastic, pharmaceuticals, even antibiotic resistance could be considered kind of an emerging contaminant. So I'm going to talk about that. So just to set the stage, I think, in my opinion, we have like some major grand challenges that are interrelated here. Soil health, big problem. Climate change, I don't know. I still believe in it. Water quality and quantity, big problems. You could add phosphorus to this list too, but they're kind of part of the soil health and the water quality and quantity challenge as well. So let's see. Becca kind of touched on the circular water economy, but I'll bring you some graphics and information from the Water Environment Federation. But their definition is of the circular water economy is that it recycles and recovers resources from the water use and treatment cycle to maximize the value to people, nature, and businesses. And biosolids or treated wastewater sludges are a major part of the circular water economy. There's a lot of resources in there to recover, but a lot of major challenges before we can do that on a regular basis. And it's not an opinion, it's not my opinion, it is a fact. And there's decades of research related to phosphorus recycling and some exciting research ongoing and into the future as to how best to valorize phosphorus and other waste residuals. So we're basically moving from a linear approach where we take, make, and dispose to one that looks more circular, where we're thinking about the end products. We're starting out thinking with the end products in mind and eliminating waste and pollution, circulating products and materials, so recycling as much as possible, and regenerating nature. So speaking of recycling, why do we bother recycling biosolids? We believe it's the most sustainable method. There's, as I said, years, decades of research on the proven benefits that address a lot of the grand challenges that I mentioned. And there are also concerns and odors, over applying nutrients, talked a lot about that this morning, and emerging contaminants like PFAS are some of the concerns. And you can see I like to use the analogy of the three-legged stool there. That's basically what we have right now for options to manage biosolids. We used to have ocean dumping. Glad we got away from that, but right now we have three major methods, some minor ones like underground well injection, but nothing major. NEBRA, along with some of our collaborators, pulled together a study using 2018 data, extremely extensive study. The website there is at the top. I would encourage you to go check out all the information that's in that database. But for the year 2018, which was selected as a pre-PFAS impacts kind of year, we're going to do this again in 10 years and see where we are. But right now, about over half of the biosolids are recycled in some way to land. About 32% goes to landfill and 15% is incinerated. So that means still close to 50% is not being recycled. Some trends since 2004, which was the last data set we collected, there are more Class A biosolids being produced. There's a decrease in biosolids being incinerated, more pressures and incentives to divert from landfills, and generally a decrease in state and federal employees looking at this since the last time. Acres permitted, I don't know if I put that in there, but a lot of times you read The Guardian and some of these other publications, they keep using this number of 70 million acres contaminated. It's in this report, but that's the permitted land area in 2018 that was permitted to accept biosolids. It has nothing to do with contamination. But all right, so we didn't talk about it. I didn't put any numbers together, but biosolids are kind of a small organic waste stream compared to manures and other organic foods like food waste. So those are much more abundant than human poop. But we still have trouble managing the small amount comparatively small amount that we make. All right, also from this National Biosolids Data Project, we did ask questions, of a whole group of wastewater treatment facilities. And you can see PFAS is in here being tested in some places, but not very much just yet. You can see a lot of stuff gets tested for. Some utilities go above and beyond and test for all sorts of other things. Also from the study, again, it's based on 116 treatment facilities extrapolated. There's some good nutrients in these biosolids that we'd like to take advantage of. Nitrogen in particular, and phosphorus as well, which we all know is limited. And as far as what crops, these are, again, it's a little bit fuzzy, but for the most part, it's the feed fodder, those types of crops that are grown with biosolids. But you can see there's quite an array of different products that are grown using biosolids. And according to this report, less than 1% of US cropland would be needed for land application of all biosolids. What happened in Maine? Andrew's gonna talk about it a little bit, and I think Emily will too, but there were major contamination issues, major sources of PFAS related to the paper industry that made their way to the treatment facilities and contaminated the biosolids. Pulp and paper mill residuals, nobody really talks about that, but that was one of the residuals that were applied to these farms, and they used to have a lot more PFAS in them than they do now. So these are legacy sites we're talking about, 20 years ago, land application. So first there were some limits and a temporary moratorium that the regulators set back in 2018, 2019 time period. And then the legislature got involved and there was a ban in 2022. And a lot of other things kind of came together. They also banned out-of-state bulky wastes, which were needed to mix with the wet biosolids in landfill to make that a safe practice. So things blew up pretty quickly. They were shipping a lot of material to Canada. It became a big press thing. It's still not solved there. They still don't know what they're going to do with these biosolids. So it's not sustainable. They don't have a long-term solution. And the treatment facilities have experienced double-digit cost increases. In the state of Maine, they used to promote composting, and the last time we did this, so this is from 2018 data, you can see the last time we did that study, the recycling piece was 60%. Now this is 60% landfilling in 2018, and right now it's 90+% landfilling in Maine. All right. Quickly, just some of the impacts. You can't see this. I was hoping you could see this map in the background, but I'll talk about it in a minute. Lots of legislative and regulatory activity in the Northeast around PFAS and biosolids. Connecticut copied Maine and also banned it. We're dealing with 1 part per billion-ish background soil levels in the Northeast. How do we deal with that? We have some of the states doing some major, like big picture master planning. What are we going to do with these biosolids? We're starting to see solids violations. So when they can't find a place to send the solids and it gets backed up, there's no storage at these facilities. There's no place to put this stuff, and it goes into the receiving body. And then the biggest thing is it's complicating the problem is the materials are being shipped further and further away from the source. So now you're using up material and people to do that. That's taking up 3 times as long as it used to. So everything's starting to snowball. Massachusetts is considering a ban right now as we meet. And so this graphic in the background is from the state master plan that Massachusetts has started working on. And I don't know if you can see, but the blue lines are liquid sludge and the orange lines are cake sludge that's going extremely far, Canada, Ohio. And it's about 70% of Massachusetts solids are going out of state. So they have a real interest in getting on top of this problem. I feel like we're hyper focused on the PFAS and not enough on some of the other real problems, but I think, new technologies are definitely a part of the puzzle. And I think Ivan's gonna dig into that later. Um, But these are just to mention a few I put phosphorus extraction technologies on there, because those are important to you folks. We also are, again, hyper-focused on the PFAS removal technologies that are emerging. Every day, something new is coming up. But the major ones are pyrolysis gasification that we've been talking about for decades and haven't been able to figure out yet. Some hydrothermal liquefaction and carbonizations that can be combined with anaerobic digestion and gets really good results there. Supercritical water oxidation, this just disintegrates everything. It's a really cool technology if they can get it, scale it up. And I just mention it because it's the minerals that are produced from that process are very rich in phosphorus. As is sewer sludge incineration ash, which we don't reuse in this country for some reason. So that's just to mention a few of these technologies. I'm kind of watching to see whether some of these legislative efforts to ban biosolids recycling is gonna put a damper or maybe accelerate research on new technologies. My big issue with these technologies is they use a lot of energy, and I'm not sure they can be sustainable. So I mentioned climate change. Again, NEBRA manages a fancy spreadsheet, basically, that can be used by the average wastewater professional to look at up to 10 different options, end use options for biosolids management and the greenhouse gas impacts of those. So I can tell you, I'll credit Andrew Carpenter and his group for helping us update that. It's based on science. We have it reviewed every 2 years by 5 PhDs. There's major credits for replacement of commercial fertilizer and carbon sequestration in land applied biosolids. And landfilling it is the worst option as far as greenhouse gases. So here's an example of a use of the BEAM, the Biosolids Emissions Assessment Model, for one of my members in Maine that went from composting, making a nice compost, to continuing to compost to stabilize it, but now sending it to landfill and some incinerators in Canada. And yeah, I showed this graph one time at a conference, a guy with a big red MAGA hat in the front, and he even got it. He was like, oh, yeah, that's a big difference. So I try to promote this when I can. The landfilling is the worst. Just trying to give you some food for thought here, and for our discussions later. I also want to mention this effort that I've been involved with in the Northeast, this wastewater residuals biohub, trying to connect new technology providers with treatment facilities that are looking to test some of these technologies. It's got a compilation of research papers, compilation of pilot projects. There's a lot of information in this clearinghouse, and we're looking to expand it to other organic residuals at some point in the future as well. But right now we're focused on biosolids. And this is a paper that we put together, the folks that are working on this biohub. It hasn't been published, but I put it up there. This is called a graphical abstract, which I had not heard of before this. We had some great students at UConn and UMass that helped us develop this paper. But you can see it talks about the problem with the linear economy, the transitional issues, and then the circular water economy, and this includes all organics. So again, food waste and stuff. We could generate 325 billion kilowatts of electricity a year, sequester 292 megatons of CO2 equivalents, fully offset US fertilizer demand, and save billions in disposal costs. The biosolids portion of that is a lot smaller. Again, I said we're only a small portion of these organic residuals. So I have those numbers if you want them. And I can certainly share this paper with you if you'd like. It hasn't been published yet, at the end of this paper, we're calling for a national biosolids innovation hub and a national resource recovery. So again, to continue with the circular water economy idea, we're really good at making struvite, but there's so many other things that we can make from the biosolids, hydrogen gas, biodegradable plastics. I'm getting blown away every day by what these PhD students are working on. So, but it's a balance. We have to balance resource recovery with emerging contaminants and then other concerns. In my vision, the wastewater treatment facility would be the hub of the circular water economy, right? We have water, clean water, nutrients, fertilizers, maybe even biogas to power your car. But we have to do some source reduction before we get to that vision. But I like to ask I like to ask the question when we talk about the circular water economy, what are the risks of not land applying these materials? EPA and the Department of Agriculture had come up with some joint principles. I don't know if Emily will mention them, but they're still online. And they include, reducing the discharge of PFAS to prevent the contamination of biosolids, preserving flexibility and availability of options for biosolids while prioritizing public health, ensure continued safety of the food supply and support impacted farmers and ranchers. So those are all great things if they can move ahead. I think we need to give regulators more and better tools. I'm hoping Emily might touch on that. Probably need a new Clean Water Act that deals more directly with contaminants of emerging concern and non-point sources and other modern day challenges that we have. But we need regulatory drivers to address this PFAS and the environment issue. But we also need what I'm calling a regulatory sandboxes, a little place to play to see if this is gonna work or that's gonna work. I don't know how we get there, but maybe Emily has some ideas. Communication is key. Words really matter. I do not say forever chemicals anymore. I just said it now, but to make a point, I don't use that word anymore. They're not forever. I don't consider them forever. And we used to call the wastewater treatment community passive receivers. I don't use that term anymore either. They're actively doing stuff. They're out there reducing concentration. So being careful about words that you use is really important. I think that's pretty much all that I had to kind of tee this up, and I believe Emily is next. Oh, we're gonna have a transition.
Yeah, we're gonna. We can have like have time for 1 or 2 questions as well, this. Ask Janine.
I actually have a question for Janine if no one else does. So Janine, yeah, I assume I don't really know. I assume there's quite a bit of PFAS in food waste as well. What about manure? Is there any reason that you would have it in animal waste?
No, not unless they had a contaminated forage situation going on. Not generally, but maybe every few months.
Yeah, I think I have it.
Yeah.
Okay.
It's very minimal.
Okay.
We have some of the contaminated farms in Maine had it, and some of the most contaminated farms, even their levels weren't that high relative to other materials that we see. But it can make its way into the manure.
Yeah, I was going to ask, is there any kind of long tail effect because of the fact there's so much more manure applied versus biosolids? Does it?
It's, most manure is lower than what we see even in food waste compost. And we've done a lot of testing on fields that have just received manure and not anything else. And have a long history of manure, and those levels are typically really close to background levels. So it does not seem to be a source unless there's something particular going on.
Okay, great. Thanks, Janine. So I should have mentioned earlier too, we're gonna hear from 4 speakers, and if there's time left over for questions, we'll take some quick questions on kind of individual talks. And then at the end, we have plenty of time for a panel discussion. So you can also save your questions till the end if you'd like. So let's see. There we go. All right, so next we have Emily Rimmel, is NACWA's Director of Regulatory Affairs and spends her time working on water quality, PFAS, biosolids, stormwater, water reuse, and other pertinent regulatory issues happening at the federal level. Emily has a bachelor's and master's degree in zoology from the University of Oklahoma and a Juris Doctorate degree from Vermont Law School. So welcome, Emily. Do you want to move around? Yeah, either Matt or the time.
Okay. All right, thank you. And thanks, Janine, for buttering me up to answer some of these really difficult questions. I hope I can do that. Just to get a scope of who's in the room, who's here from a utility or consultant or researcher, engineering backgrounds, I'm guessing. Okay, great. I'm not an engineer. I'm a zoologist and a pseudo lawyer. Okay, how do I just the clicker here?
Yeah, that works.
And I definitely remember a time before PFAS. And so when Matt asked me to come talk about managing emerging contaminants in the circular bioeconomy, I did some reflection because it's almost like oil and water, right? You've got an emerging contaminant and something that is a well furbished machine, a circular bioeconomy that works and has worked. Excuse me. And then you introduce something completely new and it disrupts the entire process. Excuse me. So that's what I'm going to talk about is really this disruption and the uncertainty that NACWA members are facing. And there was a time before we even knew about PFAS. And I remember that moment vividly when I was sitting at EPA headquarters in 2018. And then Administrator Scott Pruitt, under a Republican administration, introduced the concept of PFAS to us. And we were shaking our heads like, is this going to be something like pharmaceuticals or personal care products, something we can manage kind of in scope here? Or is it going to be something like dioxins and furans or PCBs? Where are we on this, line of emerging contaminants? And so for our members who really weren't sure about PFAS, we had to get up to speed. I had to get up to speed so fast on the background, what PFAS is, what's the scope here, and what potentially could our members be facing short and long term. And I have to say that since 2018, 2019, that pathway that we've been on from the clean water utility landscape continues to evolve. There are no short, simple answers, and it flip-flops all the time. So NACWA, the National Association of Clean Water Agencies, we represent 360 public wastewater utilities. We are in Washington, D.C. We do legislative lobbying, regulatory advocacy, and legal stuff with the courts. That's what we do on a daily basis. And so our members really look to us to help them understand what's happening at the federal level. And that's really hard when it comes to PFAS because every administration has a different way to think about this. And so as I mentioned at the beginning, PFAS has really caused a ripple. It's not just one contaminant. We're talking thousands of contaminants. We're focused on a few primary ones, but it is disrupting how we think about environmental jurisprudence. It reaches every single environmental statute and regulation that we have on the books, and trying to understand where this emergent chemicals fit into our existing frameworks is challenging. And that's why it always reminds me when I'm putting my kids to bed and I'm reading them Where the Wild Things Are, is it's a total frenzy out there. And it has been for the last 5 years, 6, 7 years. Everyone is trying to understand how it's going to impact them. Everyone thinks they're a PFAS expert. Everyone seems to try to give a solution, and it's not simple. So here's kind of the story, and I'll give you some insight to where I think we might be headed. There have been 3 major action plans introduced by each administration since 2018. And if you know about PFAS and you've looked into kind of what's going on, each one of these is so comprehensive. It talks about the Safe Drinking Water Act, the Clean Water Act, what we're doing on the Toxic Release Inventory, what are we doing on the Clean Air Act, how is this affecting CERCLA? Every single environmental statute is listed in each one of these to some degree. how are we going to go about tackling this emerging suite of chemicals? And it's been interesting to see the evolution of this process play out. The first framework, the first roadmap had a pretty comprehensive suite of actions, but it wasn't until our last administration, the Biden administration, that we actually saw um, actions. We saw promulgations of rulemakings. We saw the EPA trying to address concerns over PFAS. Now, those are changing again. So this is the flip-flop that I was talking about. And the problem when you've got such a pervasive, ubiquitous chemical that can be measured in trace amounts, how that is dealt with between administrations. And we're seeing the EPA not change its tune, but being challenged in the courts and having to kind of rethink how it's going to go about managing PFAS and public health and the environment. These were just some of the, before PFAS, I was talking to a few folks, we used to work on stormwater and nutrients and just your bread and butter Clean Water Act issues. These were the things we were confronted with immediately with these roadmaps, MCLs, human health and aquatic criteria. Those take years to do. The biosolids risk assessment, that's a big one that I'll talk about here in a minute. Pre-treatment standards for all sorts of industrial categories. We didn't even have a method on the books to test for PFAS. And under the Clean Water Act, there's a really specific process for approving a method that's consistent and we can trust. Destruction and disposal, always an ongoing conversation. But to see all these things happen at once kept us so busy. It's just been a whirlwind. And one of the big ones that is moving right now is CERCLA. CERCLA liability, I'm not going to get into the details. Have a beer with me afterwards and we could talk about it. But really having this retroactive statute that tries to hold the polluter accountable could rope in public wastewater utilities, drinking water utilities, anybody that land applies. It doesn't care the concentration, it doesn't care the timing. If this is ultimately finalized, you could face liability in all sorts of ways from private citizens, citizen suit litigations. So EPA did this, it was finalized and immediately challenged, it's still in the courts. There's ongoing federal legislation to try to protect wastewater utilities, to try to protect drinking water utilities, municipal airports, farmers, the ag community from someone potentially bringing a claim against you for CERCLA. So that's all playing out in real time, but that's a big one right now for us, in addition to all the other things. And so, has anyone seen this graphic?
Michigan Eagle.
I've seen it there. I've seen it distributed in quite a few places. There's one flaw that I see with this graphic, and I try to use this in several of my presentations. Is this is the PFAS cycle, right? Does this have a laser, right? So here's our members, the wastewater treatment plant. They often get pinpointed for their discharge. They're biosolids that either go to landfills or are applied on land. Here's all your industries using PFAS. And I mean, they run the gamut. But there's no arrow from your residential home to your wastewater treatment plant. That's why it's like blatantly not there. But you kind of get confused by all the different arrows. And so what we are trying to show is that source control can work for the industries that we know are discharging PFAS to a wastewater utility. That can work, and we're doing a really good job at the low-hanging fruits. Now, there's a lot of diffuse systems out there and manufacturers and secondary users of PFAS that don't even know they're using PFAS, and it's getting rinsed down the drain to us. But it's the residential contributions that are enough to trip a lot of these environmental statutes, their thresholds for risk and concern, right? So, who here flossed their teeth this morning? I did. That floss has PFAS in it.
Had all
Yeah,
things to
yeah,
do with it.
yeah. Paper cup, all these tablecloths, all these things, wash your clothes, all of that residential use goes directly down the drain to the wastewater utility. And making that statement and helping policymakers understand that the makeup I put on my face in the morning and rinse down the drain contains PFAS. And the wastewater utility is receiving it from domestic sources. And it's a huge contribution. I shouldn't say huge, it's a significant source of PFAS to our influent. Costs. There's been a lot of effort trying to understand what the cost of PFAS will be for a wastewater utility. One of the most significant studies that I have seen was actually done by the state agency in Minnesota, the State Environmental Agency. Destroying PFAS and removing it from a wastewater utility alone, 14 billion to 28 billion over the next 2 decades. Yet you can buy PFAS for $50 a pound. It's just astronomical, the thought that we are going to pass treatment costs on to ratepayers. There's no federal funding, there's dwindling state funding. So really what we're if you're trying to talk cost benefit, talking to policy makers, this hits home in the sense that it's going to cost a lot of money for communities, especially smaller communities, to remove this stuff if the treatment ever becomes available. So lo and behold, EPA under the Biden administration published its draft human health criteria. Comments were accepted all the way through this administration, so it'll be interesting to see how this administration deals with human health criteria. This would regulate the effluent discharge of a wastewater utility, and these are the levels that they are looking to get to. 0.0009 parts per trillion, 0.06 parts per trillion. We can't really even analytically have confidence in those levels. We can measure about 1 to 4 part per trillion reliably. So we don't know how this is going to shake out. It's still pending review. They're reviewing comments at EPA Office of Water. The risk assessment, I could have another beer with you about all the concerns we have with this.
How about a shot?
Yeah, I figured so.
Tequila. EPA's biosolids risk assessment is in draft. Comments were due through August. This is the framework that will set the tune for all biosolids regulations moving forward. It's looking at PFOA and PFOS now, but the framework really could apply to any other pollutant that EPA deems worthy of potential regulation. We had concerns with how it was framed. It used a non-typical, not really practical farm family. It assumed a farm family never left the farm. They ate everything on the farm. They drank water from the farm. The fish from the farm pond was part of their diet. Eggs from the chicken, part of their diet. They never left to go to Arby's or McDonald's or wherever you potentially like McDonald's, whatever. So it wasn't really practical and it was obvious. So we flagged a lot of that, and it assumed a starting point of a 1 billion part PFOA, PFOS concentration. So if you have 1 part per billion in your biosolids, you're going to have a risk to your typical farm family, is what it says. And that's being used out of context. Show this slide here in a second. It's unclear where this is going to go. EPA called us in, a couple other stakeholders from the agricultural community, to talk about practicality. of what the draft framework might result in if finalized as is. The farming community stood up and said, this is not how we farm. There are all sorts of things that you didn't consider or you considered incorrectly. So it'll be interesting to see what EPA decides to do, whether it withdraws the previous administration's draft risk assessment, whether it finalizes it without a numeric kind of number attached to it, and maybe makes some best management practices, whether it moves forward. And the next step in the risk assessment framework is to conduct a comprehensive sampling to see if we even need Part 503 regulations. So it's a long game. Unfortunately, states are moving forward without the US EPA. They are starting to legislatively take control and regulate biosolids land application, as Janine mentioned. Maine was the first out of the gate. We've seen a lot of others try to follow suit. None of them as drastically as Maine, but it's the effort is there. And so the states in light green are all states that have similar legislation that would regulate away the land application of biosolids. I said floss earlier. Toilet paper, guess what? PFAS contains, you can't really see it with the lights here, but
Here. Oh,
yeah. So going straight to the wastewater utility, and it's everywhere. I mentioned source control can work. Michigan's doing a really comprehensive effort to try to mitigate industrial sources of PFAS, which would then mitigate PFAS coming to the wastewater utility, mitigate PFAS in biosolids. You can see here, these are before they started really trying to do industrial pretreatment. You have quite high levels. This is part per billion from coming into the wastewater utility, and then after they did some pretreatment efforts for industrial users, you cut this drastically, 88%, 98%. Those are the known PFAS sources, so you could probably even get those a little bit lower. Last few slides here, just to reiterate the domestic concerns. This is the Bay Area in California. They don't have a lot of industry. They have 95% of their flows are from residential and commercial customers. And they're finding that most of their PFAS hits are not from industry because they don't have much industry. So their background levels are coming from their domestic sources. So their really only solution is we've got to get this stuff out of our commercial products. Oh, yeah. Thank you.
Yeah, so my question's a little bit more on the like policy philosophical side. So, there's these big regulating bodies which control like different aspects of the market. So like FDA, USDA, EPA, and I understand why so much focus gets put on water and wastewater because it's so much easier to regulate, right?
Point sources.
Yeah, so who would be the regulating body who would tackle these like consumer products? Like when we talk about lead in paint or aerosols
Yeah.
in consumer products, like who's moving that needle?
Yeah.
Or do they exist?
Yeah, well, that's an interesting question because the silos that exist in DC are complete silos.
Yeah.
On the biosolids question alone, you would think that USDA and EPA would be holding hands on this walk together. Nope, they aren't. And we are asking them, the farmers are asking them to get together and talk about how we can do this.
Okay.
For consumer products, it's FDA, it would be, Food and Drug Administration, I mean, the food paper packaging. You're seeing states like California do a really good job at passing their own state laws that prevent PFAS in certain products, cosmetics, food paper packaging, but there's no comprehensive effort to get this stuff out of commercial goods. And that's what's so striking when you think about emerging contaminants, like PCBs. Like, we did this before. It's not, we should be thinking holistically, but because it's so many chemicals and they're in everything, I think that would be a Herculean effort.
Thank you. What else?
I have a question. In terms of the treatment technologies, wouldn't we be just transferring it between phases?
I know Ivan's gonna answer that question because he's gonna talk about technology, but that is a huge concern. We've been trying to get data on folks that are advertising complete destruction of PFAS, and they're a little sketchy about telling us whether or not it's in the air to some trace level, escaping some way or another. But yes, that's the big concern is that whatever's out there for treatment, you're just passing the buck in some way. You're always going to have like a residual. Even the drinking water folks are dealing with that. If you're using granular activated carbon, it's just in the carbon, and then you've got to regenerate that over time, and you can, so it's complex. There isn't one solution that's going to solve our, at least yet, scalable to a wastewater treatment, millions of gallons a day.
Yeah, for a major city.
Yeah.
So I know on other topics, I think even nutrients, EPA and USDA, they've even us at one point in Water Research Foundation, we had this MOU, right, to address and commit to work together. And I'm not saying much came of it, but is there any talk of any sort of MOU in this arena at all?
I mean, Janine mentioned there's a,
That was in the Biden administration, but it's
Yeah,
on the website.
it's still on the website. We've not, and it's tough with this administration not wanting to pass new regulations, focused on science and gold standards, and so it's, they're withdrawing certain aspects of previous administrations' rulemaking. So it's hard to see an MOU right now.
Hey, okay, one more.
I'll allow it.
I'm gonna use the microphone so I see more authoritative booming voice. Am I naive, or could the ratepayers and utilities sue the 3Ms of the world?
Some are, right, in the drinking water context. Communities faced with really having serious industrial contamination, like Wolverine was in, I believe this is in Michigan. I think the gentleman from Michigan just left. They sued the manufacturer of Wolverine for applying Scotchgard to their boots and then selling them and contaminating groundwater. They're going to receive money, one would hope, to address that, compensate them for their injury in whole. But as far as I'm aware, the mass litigation over liability is not, and some are committing to it, some are joining, is not going to be enough to deal with PFAS in perpetuity. So it might help you invest in treatment at a local scale short term, but it's not enough to help you as a utility to deal with this long term. So you kind of had to hedge your bets if you were going to enter into that agreement, but we didn't really advocate one way or another, because we just don't think it's enough money, and then you can't come back to the manufacturers again and they're absolved, right? So it was kind of a risk, but some utilities are going to get some money to help with contamination, but I don't know if it's a long-term solution.
Okay, and I think some of those questions would be really nice for the panel, thinking about time frame and the fact that we still have new sources of PFAS being manufactured at the same time as we're dealing with all these issues. Okay, so up next we have Andrew Carpenter. He's a certified soil scientist, certified crop advisor, and certified nutrient management planning specialist. Andrew has been recycling organic residuals and developing recycling programs for byproducts outside of the traditional recycling market since 1992. He founded Northern Tilth LLC, an environmental consulting firm focusing on organic waste management and building soil health in 2003. Andrew is currently a trustee of the Compost Research and Education Foundation. So we're excited to have him share his expertise with us today. Do you want this?
Yeah.
Okay.
What are the new glasses used?
Like them.
I look good in them, right? How much time do I have? 20 minutes? Yeah, I'm gonna watch that. So is this on?
Yeah.
You guys can hear me? We need monitor speakers up here. As a company, we do a lot of work with a lot of different types of organic waste that are used as byproducts, and typically, just historically, because of the projects I work on, I get into contaminant issues a lot, and chemical characterization, working with new labs so that we can figure out who can actually test for some of these emerging contaminants. And so when PFAS did become an issue in biosolids, and my background is I got into soil science, nutrient management planning, and all of this through in agriculture through biosolids because I was interested in the idea of using these byproducts to build soil health and displace the use of commercial fertilizers. So I've been in it for a while, and my role is often trying to get ahead of some of these issues on emerging contaminants. So when PFAS did come up as an issue in biosolids, it was first brought to my attention sometime around 2015. We got in pretty early on trying to find labs that could actually quantify PFAS in biosolids, developing protocols for testing for it because it's so easy to cross-contaminate because it's in so many of the materials we use. But as a result of that, when things did get really hot and heavy in Maine in 2019 and through 2021, we already had a fair amount of experience with it. And we were hired by a lot of different entities to do a lot of PFAS testing on every kind of media, environmental media that you can imagine. So compost, biosolids, manures, soils, milk, kale, everything that you can possibly imagine. And we were hired by the Department of Ag, we were hired by farmers, we were hired by biosolids land appliers. And actually a lot of the funding that did a lot of the testing, that paid for a lot of the sampling and analysis that we did the sampling, not the analysis, came from essentially grassroots raised funds from a combination of the Maine Farmland Trust and an organization called the Maine Organic Farmers and Gardeners Association. So with all of that, we have, as a company, a lot of experience in helping to, a lot of the value in what we provide when we're testing is not so much the sampling because anyone can do it if they follow the proper protocol. And the analysis is done by labs that we don't have anything to do with, but it's really a matter of putting the results into perspective. And now, even more than that, when there are levels of contamination of concern, helping farmers determine what they can and can't do, where there are more risks for growing crops and where there are less. So what I'm gonna try and do is talk you through different levels that we've been seeing in different things. So I think one of the big problems with PFAS is putting it into perspective because it is ubiquitous, very rare for us to test soils no matter what the history of the soil and not get detections at low limits for a lot of these things. Doesn't mean contamination. So anyway, that's what I want to do. Emily mentioned that there are a lot of people that purport to be experts. I've probably made that mistake of thinking of myself as an expert, but I've made so many mistakes along the way. It's really a fast-moving process that we're continually learning. So I wouldn't call myself an expert, but I call myself someone who has a lot of experience and interest in looking at PFAS in different environmental media. And I could, if there were like a lot of sessions for us to talk about beers, I could tell you about some of the good stories and the mistakes and the bad stories later, but not right now. One point, the US Composting Council hired us to put together what they call a PFAS toolkit that help people in the compost industry have sort of a little bit of a sense of, again, putting PFAS into perspective to some extent. This is one of the tables that we came up with. Probably it would be updated now. We have more information, but one of the things is, in general, it's true that PFAS is in so many different things. PFAS is not new. There's a lot less of those the two most toxic compounds, the two that we know most about now than there was 20 years ago. But our knowledge of where it exists is changed, and certainly the public perception of it has changed. But microwave bags, you probably heard this, concealer cosmetics, these are all in parts per billion. Now this is important. Every unit I'm going to be talking about is parts per billion, unless I talk about milk. And that's typically what we're reporting in when we're talking about solids, whereas water, regulatory limits and all of that are in parts per trillion. Very easy for the press to confuse the two, to conflate the two. So yeah, dental floss has some. It's not enough that it stopped me from using dental floss. What I think is interesting, and this is often true with, biosolids are such a mirror of what we use in society. We see all the things that are in commercial products regularly, we're going to see in biosolids. But household dust is another one. And household dust levels of all these different things that we look at, polybrominated diphenyl ethers, and personal care products and stuff like that, typically are going to be in higher levels than we're going to see in biosolids. And obviously they're a direct exposure. So these are a couple studies. This one study that looked at household dust from basically a survey. Those are pretty high levels. Those are higher than what we see in biosolids, in contemporary biosolids typically. There've been in Maine, New Hampshire, Vermont, there's been a lot of background surveys of uncontaminated sites, so we have a sense of what levels we're gonna see in soil when we sample it, and these have actually been really close to what we've actually seen in the field. There's almost always detectable levels, especially of PFOS in uncontaminated soils, and PFOA to a lower extent. This is what I think one thing that's fascinating is if you look at the blood serum levels, average blood serum levels in the US population back around the turn of the century, or the 2000 turn of the century, versus now, they've dropped for both PFOA and PFOS, they've dropped by about 7 times. And that's related to the fact that we have phased out of production those two to a great extent. So that actually has been quite successful. So most of the problems that we're looking at with those two compounds, which again are the compounds, those are two of the circlet compounds, those are two that we have more data on toxicity about and more sense that these do have some potential toxicity in some of the lower chains. Our exposure to them, if it's not a direct exposure from a contaminated site, is much lower now than it used to be 20 years ago. If you look at compost, food waste compost tends to be a little bit higher than leaf and yard waste compost, and it's pretty clear by now. There's been enough sampling that's been done to demonstrate that this is coming from the packaging itself, and in some cases the compostable foodware itself. So I have actually some good data on that I'll show you if you don't get bored of numbers by then. Biosolids composts tend to be higher because we do have a certain load in the biosolids themselves. This is just, I always find this fascinating. This is PFOS in blood serum levels. This is a 95th percentile, but here's the average. And you can see how it's decreased across over time recently because of the reduction of these in commercial products, because there's been some bans. I don't even know the extent of the bans or how they're enforced. We know there's still some out there, but there's a lot less than there used to be. There are, of course, replacements, and we need more work on those. So this is interesting. I gotta say, for me, working on this, there were 2 or 3 years where we're a small company. There are only 11 of us. For 2 years, essentially, when PFAS went off the charts in Maine, we were in ground zero. It became almost 30% of the work we did. It was very hard for us to scale up to it, but more to the point, it was an incredibly emotional issue. And part of this is because of my background in biosolids. But these are 3 farms, so we were the company that did the testing in a lot, for a lot of the newspaper articles that you read about coming out of Maine. That was testing that we performed. We were then responsible for talking to the farm and saying, yes, these are incredibly high levels. Your farm is very contaminated compared to what we see elsewhere. Very emotional issue for us and for me personally. These are all 3 farms that are in my county where I bought products from, including this one that had pretty highly contaminated milk that I used to make yogurt. I still do actually, yogurt out of their milk. These are all farms that would meet that. They would be that family farm, the worst case scenario. And just, it so happens I'm in a little bit of a bubble, a lot of back to landers where we live. But I have argued when I've heard people say that those scenarios are unrealistic. There are 5 just in my county that essentially live that lifestyle that's reflective of that worst case scenario, that family farm. And the ones that had really bad contamination did get their blood tested, and it was extraordinarily high. And these farms, now they're all good friends of mine because we sort of have gone through this process together. Of course, it was a lot harder for them than for me. 2 of the 3 of them are back up and running and doing great. One of them, which was the worst case scenario, this was the very first one that we found with really high levels. They sold the farm. They're ones where their blood levels were very highly affected. They're getting monitored on a regular basis for potential problems that might come from PFAS. But they were an organic vegetable farm. They were also growing organic grains, which is pretty rare for us in New England. Both their soil levels and their drinking water levels were high. They were growing all of their own food. They ate a lot of greens, which have a very high uptake rate. This one's the one that I bought that we still buy the milk from. Very diverse farm, so they had it in milk, but they also had it in some of their other products, their meat products as well. And then this one was probably the easiest. It was a organic vegetable operation. They hadn't been there that long. Their water levels were really high. The soil levels were not. The soil levels were a little bit elevated, but that just came from irrigating the land with the well water. All of these, the contamination, all of these came from biosolids that was from a municipality where 50% of the flow to that municipality, and actually my grandfather, my wife's grandfather was an engineer at this mill. They made paper plates, ironically. They coated the plates with some sort of PFAS. And so it was foodware they were making that made the biosolids so high that it actually contaminated the ground. And none of these farms used the biosolids. They all bought the land afterwards. So one of the things we look at, is soil loading rates. So what is a material what's it gonna add to the burden of PFAS in the ground if it has PFAS in it? It's a simple equation that we work on all the time, and don't focus on all of these numbers. I feel like I'm missing something here. Okay. This is pretty typical for us. If someone has some PFAS in their compost, we want to look at what impact it's going to have by using that compost on the soil. In this case, we're looking at food waste compost that has a concentration of PFOS of 5.2. That's a little high. We don't typically see that in food waste compost, but it's not out of the range. Applied at 20 wet tons to the acre, and we assumed that the concentration of that soil was what we see as background levels for PFOS in New England, 0.5. If we add that 20 tons per acre, we're going to see, in theory, that concentration go up to 0.53 from 0.50. Something that we wouldn't be able to actually see in the precision or lack of precision in testing. Really not a big deal. If you did it every year and it always stayed up that high, you'd start to see a little drift, but these are very low levels. This is that farm that I talked about that actually did go out of business. We actually know from records exactly how many dry tons of biosolids were applied to this field. It wasn't that many. It was 52.8, essentially 53 dry tons over the course of 4 or 5 applications. This is their current soil concentrations. So from that, I was able to back calculate. This is making some gross assumptions of no degradation of or transformations of PFAS, which you know are going to happen. But in that biosolids, the level of PFOS must have been somewhere around 7 to 10,000 parts per billion. So way off the charts of anything that we see currently, unless you have, you know, if it's a facility that happens to be treating wastewater from an industry that's manufacturing it or using it in the manufacturing process. So this, and to me, this is very important. The difference from, okay, these are levels that we might find in contemporary compost, and this is what the soil was, we know would probably be like beforehand. These are typical application rates. The stories that you hear coming out of Maine, again, some of which came from the testing we did, it came from a material that was very highly contaminated. If you look at contemporary levels of biosolids, we do in what I put together, and this is, I say don't cite or distribute. I got this from regulators in different states. It's not an official document, but we have pretty good data now, and we're getting more and more over time of how much PFOA and PFOS and some of these other ones are typically in biosolids with that typical residential load with no real big industrial input. And this is what we see, PFOA levels typically between 1 to 5, and PFOS levels typically between maybe 10 and 25. That's contemporary biosolids, they're pretty much in there unless they're industrially contaminated, like the ones that Emily pointed out, for which there has been a fair amount of success in actually finding those inputs and reducing them. So at these levels, these are kind of the levels I was showing in those calculations. Unless you're using it 10 years in a row at pretty high rates, you're not going to move the needle too much on soil concentrations using that material. One of the things, though, I'm doing on time. Good. 5 minutes left. Oh, there's so much more to say. I'm gonna cut it. I'm gonna move through it though. I'm gonna be good, and I'm not gonna waste time talking about how much time I don't have left, because that would be really unproductive. So let's just move forward here. Biosolids 20 years ago had levels that were much higher than they are now, and they probably mirrored what we've seen for that reduction in blood levels. So the assumption is, and there's been some testing that has proved this from archive samples, it was probably about somewhere between 7 to 10 times higher than it is now for PFOS and PFOA. So if we look at in New England, and I'm sure in a lot of places, we have a lot of farms that have used biosolids for 30 years, and sometimes they've used it on the same field every year for 30 years at agronomic rates, so not high rates. But when the biosolids were higher, this is what we've typically seen at long-term land application sites that are getting it from year to year for, and this is PFOS, somewhere between 5 to 15 parts per billion in the soil. If it's someone that just used Class A once, like something they actually purchased, we might see a little blip above background levels, but we're not apt to see that much. But these are the levels we're seeing in the soils from that one, from the farmers that used the material from that one site. Even though they weren't using a huge amount of it, it was just so concentrated that it was high. We do have, I can't go into all this, but we can talk about it later. We do have some risk-based guidance levels in Maine. And I will say, as much as the legislator overreacted in putting the ban in place, the Departments of Environmental Protection and the Department of Ag and the CDC in Maine have really been great in following up with these farms, trying to determine what levels are bad, what aren't, what they can grow, what they can't grow. And it's, from my sense, it's been a big success. Just talk briefly about, I mentioned that I tend to get stuck looking at contaminants in different types of soil amendments. I'm drawn to it for some reason. This one is so different than the other ones that we've dealt with in the past, and especially in terms of organic compounds. So typically with the organic compounds like dioxin, PCBs, even polybrominated diphenyl ethers, these are immobile compounds that stay in the soil for long periods of time. They may have a long half-life, but they're not moving around. Once they're in the soil, they're pretty much sequestered there until ultimately they do break down. And then more volatile things, like maybe some of the pharmaceuticals personal care products, they break down pretty quickly. So they're also not as much of an issue getting into crops or getting into groundwater, which has been the big issue for PFAS in Maine. PFAS does both. It sticks around for a long period of time, but it's always sort of sloughing off a little bit into groundwater, and the risk levels are so low that just that little bit that's getting into the groundwater can be a big issue, and same with crop uptake. So it's not, where in the past we've had these sort of principles like, okay, yeah, it's a big organic compound that's lipophilic and it absorbs the solids, it's going to stick in the soil, it's not going anywhere, or it's something that's relatively volatile or has a short half-life, it's not going anywhere. PFAS isn't going where, not a lot of it's going anywhere, but it's sticking around for a long period of time, and enough of it is mobile, environmentally transported, that can be an issue. I'll tell you one anecdote, and then I'll try and get to, well, two more things, but it'll be really quick. MOFGA, the Maine Organic Farmers and Gardeners Association, has a very big fair every year. It's very popular. It's their biggest source of revenue. It's the biggest ag fair in Maine. And they, at one point, told they're very strict with their vendors. The vendors can only use certified organic ingredients, and you couldn't, until a while ago, and maybe it's still the case, you couldn't even buy coffee inside. Like, I don't know why, but there was a guy outside that would sell coffee and make a mint. But they told all their food vendors that they needed to use compostable foodware, because they actually compost the food waste from the fair there. Anyway, after we got into this, and we were working with MOFGA anyway, they had us test they have volunteers do the composting, and they actually tried to separate sort of the paper fiber stuff that was compostable from the actual food waste. So they had two piles. So one of them was a worst case scenario potentially if there was PFAS in the compostable foodware. So they had us test that and the regular food waste compost, and in fact it was quite high. It was higher than we typically see in, oh shoot, where's my pointer?
Top one, very top.
Oh, that. Funny how quickly I forgot that. I see it. Yeah, the levels in here were higher than we typically see in contemporary biosolids, and this was the compostable foodware that was certified for use in this kind of thing. They've made great strides on finding out what the sources were. It tended to be, it looks like it was the bowls in fibrous, like wood-based or fiber-based compostable foodware that had relatively high concentrations. But it's surprising, unintended. Oh, and we did test the manure there because they were putting some of the manure into the compost, and it was detectable, but it was incredibly low. And that's typically what we've seen with manure, unless it's a farm that's sort of recycling it through their grass and manure. I'm not even going to go into this because I'm at the end. I will say, we also got a grant from the NRCS, USDA NRCS, to look at, now a lot of our focus when we're working on PFAS stuff, we're not a PFAS company. We just happen to get into this a little bit. A lot of the focus on the farms that are contaminated is trying to determine what they can safely grow. We found, and the CDC has been really helpful in this, it's some of the most highly contaminated fields we've seen, there are non-detects when you're growing grains, including corn, wheat, and things like that. It just does not transfer to the grain itself. It does transfer to the shaft, the stalk. But grass has been one of the biggest areas of concern. The transport from soil, contaminated soil, to grass, to cow, to either milk or beef. That, for PFOS specifically, has been a big problem in Maine at these contaminated sites. So we got a grant to look at using soil sorbents, incorporating soil sorbents into some of these contaminated soils, growing grass there and seeing if we could reduce the uptake of PFOS. And we're working with Linda Lee from Purdue University on this project, and we had real success in the lab. Oh, and these are the sorbents. We use biochar in some, and we use high carbon ash in some at rates that nobody would typically use, very, very high rates. We had 95% reduction of uptake of PFOS in grass in the field study, which was these soils and these same amendments, but sent to Purdue. In the field study, we've had a little bit of reduction, but it has not been nearly as promising as the greenhouse trial, and we have a lot to learn. I think it has to do with water dynamics more than anything. And oh yeah, the thing about PFAS too is it's not like Janine said, it's not forever, and in some ways it's even worse than that, because there's some of its precursors that can be pretty high in some of the materials we work with that actually at first are not the compounds of concern. They're not PFOS or PFOA, but those two are terminal products, metabolites of some of these larger compounds. So you can actually, under certain conditions, increase the concentration of those two by transforming some of those precursors to those terminal products. And composting in an aerobic environment does in fact do that in some cases. Composting does not degrade it. If it does, it's very limited, and it might do it on the smaller ones. But for the chemicals of concern, you can actually see on a mass balance basis a little bit of an increase in PFOA and PFOS during the composting process. And I think I gotta end it now. Yeah, I'll just say my passion, the reason I'm in business and what I do, my mission is really to use organic matter-based byproducts to build soil health and reduce the use of chemical fertilizers. This has been a huge challenge for us and for everyone that's in the business.
Probably save questions till the end because we're kind of running short on time, but we'll have plenty of time with the panel, so I'll just save them till then. So, which mic to use here? For our last speaker, we have Ivan Cooper, who is a principal at Civil and Environmental Consultants in Charlotte. He designed over 100 leachate industrial and municipal wastewater treatment plants, including treatment plant designs for PFAS removal. He has a BSCE from Union College and a master's in civil engineering from Northwestern University. He is a registered professional engineer in 22 states and is a board certified environmental engineer from the American Academy of Environmental Engineers with a wastewater treatment specialty. So welcome, Ivan. You can see. You want to move around or?
Sure, I'll take this.
This
Shall
one.
we?
Then here, just advance the next slide there, and then that little button.
Okay, well, thanks. Recognize that I'm standing between you and the reception, so I'll try to make this as quick as I can, but I don't promise that. So we're taking a look at phosphorus. However, I wanted to address PFAS and a couple of areas, and I'm going to talk about emerging contaminants. What are they? Regulatory and what the environment is for regulations. And then took a look at some of the technologies associated with PFAS removal and destruction, the costs associated with that, and some summaries. Here you can see two 8-chain fluorine compounds, PFOA, which is carbohydroxyl end, and sulfonic acid, which has a sulfonic or sulfur end of it. These are long chain, typically 6-chain or less is considered a short chain. They're harder to remove and harder to destroy. The longer chain, 8 carbons or more, are considered probably a little bit easier to remove. So what are some of the emerging contaminants we look at? 1,4-dioxane, which is an industrial solvent, is pretty difficult. Microplastics and nanoplastics are getting a lot of information about those lately. Here's another one, 6-PPD. Have anyone heard of that? Yeah, that's a tire. It's added to tires to prevent oxidation wear. When it's exposed, it turns into 6-PPD quinone, which is very, very toxic to a lot of fish. And then we see it in a lot of stormwater associated with highways, gets into the stormwater. If somebody uses that for water supply, it can get into the waters. And it's particularly toxic to coho salmon. The Northwest is a very, very high interest area of that. We've talked about PPCP, the pharmaceuticals and personal care products, both in humans as well as animals. Probably only 40–50% of the drugs that we take are taken up within the body, and a large portion of that is excreted. Interesting, PFAS can be a component of the PPCPs in terms of, like, for example, gel tablets are used, PFAS is used there. It's interesting, mercury is also used in some of those, as well as some or other volatile organic chemicals. Cyanotoxins associated, for example, with algal blooms. Phenols are common in a lot of industrial chemicals. PCBs that have been around for quite a while, and of course, we look at PFAS. So these are some of the things, some of the technologies we'll discuss remove some of these emerging contaminants, some don't, but talk about those. On a regulatory basis, there's both the federal as well as state and local components to that. In terms of the Resource Conservation Recovery Act, there was two recent proposed definition and listing of certain PFAS. Those are on hold, according to the current administration. Under circular, as we mentioned, July 8th, PFAS to PFOA and PFOS were considered as hazardous substances, not hazardous waste, and there's a distinct difference. However, that probably is going to be challenged by the current administration, and that we see that maybe eliminated. There's also challenges in the court about those. EPA did issue Plan 16 for the effluent limitation guidelines. That's going to be very litigious. And we see that perhaps 2029 to 2031, for example, landfills may have to do something with landfill leachate to remove PFAS. And that's a really significant contribution to the environment, both surface water discharge as well as inclusions to wastewater treatment systems. Safe Drinking Water Act, that's that regulation that was earlier this year that's partially been rescinded, and the original date of 2029 was probably going to be scheduled for maybe 2031 for the elimination of PFOA and PFS in drinking water, and some other constituents. EPA's probably going to pull back on those. The NDAA, the National Defense Authorization Act, the current one for 2025 and 2026, there's a number of components there that affect not only the military, but also a lot of other commercial and non-military aspects for PFAS. There's a number of, there's probably hundreds of different authorizations in there. Discussion. One was the intentionally added PFAS to hazardous substances under military operations. That's probably going to be rescinded. There's a rollback of the AFFF, the aqueous firefighting foam, that's looking at that being rescinded. So the point is that under the current administration, there's a number of rollbacks of PFAS removal and PFAS control, and that just adds to a level of uncertainty. On top of that, various states have enacted a lot of different PFAS rules in terms of intentionally added PFAS to commercial products. Some states, well, probably a third of the states have some either adopted or in the process of looking at limiting intentionally added PFAS to commercial products. As well as on a local basis, a number of utilities have been banning or limiting PFAS in terms of industrial components, landfill leachate concentrations, as well as there's a lot of litigation going on for private activities, as well as EPA and the innocent receiver. I know that you didn't like the term, but innocent receivers of PFAS. There's a lot of activity from some of the in the Senate and the House, trying to pass some regulations to alleviate some of those innocent receivers, the wastewater treatment plants, water systems, firefighting agencies, and whatever. So we tell our clients, start planning on that right now. So if there is PFAS in, for example, landfill leachate, industrial discharges, or water and wastewater systems, what can be done? So I'll list a couple of those. In any of these activities, it really needs to have a chain of activities. What I mean by that is we look at separation to concentrate the PFAS from the media, and then how to handle that more concentrated residual. Very, very difficult to have a one-step process. So we look at some things that can be for segregation and then destruction. Some of the absorptive technologies include activated carbon, which is really good, for example, for water supplies or groundwater, which is fairly clean. Industrial and landfill leachate, it needs a lot of pre-treatment before that would be effective because the amount of change out would be really, really intensive. Ion exchange functions fairly similar to activated carbon. It's more expensive, but it has a lesser amount that needs for the same volume of PFAS. There are certain polymers that have the ability to remove PFAS from a liquid stream. Modified bentonite from a source in Wyoming. It's modified by a company called Setco that has ability to absorb a significant amount of PFAS. There's Vic Media, a compound called nanosorb that the company ECT2 is looking to add to wastewater treatment that agglomerates PFAS into the activated sludge flocks at wastewater treatment plants, and then that's removed from the liquid stream, but it's concentrated into the solids. This physical separation technologies, for example, reverse osmosis, works really well. It removes not only PFAS, but a lot of other constituents, but you end up with maybe 20% of the flow as the reject. So 80% is going to go out, but now you have 20% of more concentrated flow to deal with. Foam fractionation has a strong ability to absorb PFAS in the liquid stream, generates a very, very small amount of a concentrated amount, probably somewhat less than 1%, is less than maybe 1/10% of the incoming flow. But it doesn't do anything for any of the other constituents. It's really focused on PFAS. Deep well injection, various areas of the country worked well. For example, in Ohio, Michigan has good geological formations. Oklahoma and Texas are pretty good. California is also good, but then you deal with regulatory environment. It's really difficult to get anything permanent. California. Aqueous electrostatic concentrator is another process that's being developed, and that has the ability to selectively adsorb PFAS on media. Now you have a concentrated amount. What do you do with it? So you look at some management or destruction technologies. Supercritical water oxidation is basically a fourth state of matter, not liquid, solids, or gas, but it's a supercritical formation that you'll see above 374 degrees centigrade and 3,200 psi pressure. Water will enter a fourth phase that basically has the ability to destroy virtually anything organic. Low temperature plasma has been used. And there's a number of other technologies that are coming out almost weekly, we see from some manufacturer or some university that says they've got the golden answer. But those are really limited because of the state of development. Well, once technology is going to be evaluated, you look at, there's a lot of other characteristics you have to look at that. The flexibility, how is it going to adapt with changing regulations? For example, if the implementations get more stringent, can that technology adapt to that? What are the costs associated with that for the replacement media, for operation and maintenance? What kind of training is going to be needed? Some of these technologies are very sophisticated and needs a lot of training to operate well. Operator friendliness, what's involved in it? You have to monitor that frequently. What kind of testing is involved? How about ease of installation? Will it fit into a component of an existing treatment facility, or does it have to have a separate facility associated with that? So those are some of the aspects that we look at. In terms of the individual technologies, and I've got about 20 additional slides I'm not going to go through because of time involved here, but they're in the presentation, and it's almost a cheat sheet on each individual technology. What are the pros and cons and costs associated with those? So if you're interested at some point, you can take a look at the presentations at a later date. Activated carbon is really good. It does good ability to absorb not only PFAS, but a lot of other constituents. Typically, it's going to have 2 vessels. There may be some pre-treatment involved, and they looked at about a 15-minute empty bed contact time. And then when that carbon is adsorbed, it can be regenerated, and extracted out in a remote facility and then placed back new carbon to a unit. Ion exchange resonance functions fairly similar, but instead of 15-minute uses about a 3-minute empty bed contact time. So the vessel is going to be smaller, but the media itself is more expensive. Reverse osmosis works well. Again, it's a power hog. You have to have a lot of pressure, 1,500 psi. So the power cost is significant, and it generates maybe a 20% reject flow. So you have to do with something. Heat well, we mentioned that. You have to have also a fairly high concentration of power. Not concentration, but power demand. You have to get it to 1,000 psi roughly to inject it into the formation, maybe 8 to 10, 12,000 feet underground. It also has to have some pretreatment. For example, if there's barium associated with the flows, barium sulfate has a solubility of about 5 milligrams per liter. So you have to remove some of the constituents because you don't want to foul the geologic formation. Evaporation is another technology that we've seen be used well. Some of the vendors have been saying that we can capture 90, 95, 98% of the PFAS or more that doesn't get evaporated into the airstream, but the liquids do. And then we mentioned foam fractionation. It's a really good concept. Some of the residual technologies now, we've concentrated the amount. What are we going to do with it? Incineration is a potential option. It was banned for quite a while because of the concern with what are we doing with residuals in the off gas? Are we destroying that? Are we changing into the other concepts? Some of the precursors may end up, as we mentioned before, changing into terminal PFAS constituents, and there's a lot of investigation needs to happen with that. Plasma has been proposed and works in very few environments, and it will destroy the PFAS. Change sequentially to from longer chain to shorter and shorter chain to get potentially some mineralization. Supercritical water oxidation. And here's an example of some of the processes involved in that. It needs a fair amount of energy to get up to that 374 degrees C and 3,200 psi pressure. So it can be an energy hog to get it up and running, but if there's significant organics in the process flow, it can be sort of self-sustaining. Electrochemical oxidation with generation of hydroxyl radicals can metabolize and destroy some of that PFAS constituents, break that apart because that fluorine carbon bond is one of the strongest in nature, and it really bonds very tightly. So you need a lot of energy to break that apart. Mentioned about deep well injection. Some other technologies like the proposed HALT process, hydrothermal alkaline treatment, also has the ability to destroy PFAS constituents. So not that it's a forever chemical, it's forever unless you have a lot of things to do with it. We didn't work with some stabilization of PFAS, example for landfill concentrate from foam fractionation. And we found 98 or 99% of retention of PFAS in a solidified mixture. We let it stabilize with Portland cement and let it sit for 28 days. And we broke it apart, ran some TCLP, toxic constituent tests, and then ran 1633, method 1633 for analysis of PFAS constituents. And we found that we retained a significant amount of that PFAS, again, 90, 95, 98%. The amount that comes out is relatively small and much lower concentration than even what we see in raw leachate. So the point is, if, for example, with landfill leachate, if we stabilize that with cement and put it back into a landfill, the amount that comes out is going to be significantly less than what would be in the PFAS of the landfill leachate to begin with. So we feel that'd be a good answer. Wholesome Concrete has another process where they're taking that and blending it, the cement mixture with landfill leachate and spraying it on the surface of a landfill for alternate daily cover of ADC. So some of the constituents that can be returned to the landfill. Landfills have the ability to sequester PFAS, probably 70, 80, 90% of the PFAS that comes into a landfill is going to be retained within the mass of the landfill. So that has the ability for some of these concentrates, for example, in certain areas where liquids are allowed to go back into the landfill, the reverse osmosis reject can be placed back in the landfill, and a significant portion of that more concentrated amount can be retained within the landfill mass, or haul off to a very expensive option of disposal of the hazardous waste landfill facility. Currently, we see almost weekly there's some new technology that comes out of the manufacturers or university environments. There's just a tremendous number of companies involved in this. They all see this as a really golden egg for them. So it involves a lot of evaluation of the technology to see what works and what doesn't on a long-term basis. What I did, I put together a number of the technologies in the range of practicality versus the stage of development of those. And here's an option that look at some of the ones that or have more ability to remove PFAS from industrial facilities and landfill leachate and even wastewater treatment are up in this other area. Some of these technologies work really well for smaller flows, either an industrial flow or landfill leachate. Once you get into wastewater treatment that has millions and millions of gallons a day of flow, it's much more difficult and much more expensive. So what we did was we looked at some of the comparisons of the technologies, granular activated carbon, ion exchange, reverse osmosis, foam fractionation. Those are the concentration technologies. And the destruction technologies of electrochemical oxidation, supercritical water oxidation, hydrothermal technology or plasma. And we are rating them in terms of the ability for the different characteristics, the applicability, does it work well, does it energy costs, operation maintenance, and the ability for breakdown, what are the gaseous emissions associated with those. So here's a very brief evaluation of different technologies and the applicability. We also take a look at some of the costs associated with those, and we've looked at one case where we had a variety of technologies, clarification and granular activated carbon versus foam fractionation versus reverse osmosis. We looked at the capital cost, 50% less and 15% more. And we brought that back with the operation and maintenance to show the cost per gallon of treatment, and it can be significant. We looked at annual operation and maintenance cost, and we even looked at zero liquid discharge through evaporation. It can be significantly expensive. Looked at another landfill, also from evaluation of different technologies, and we came up with the cost associated with PFAS removal, and it can be actually significant. We also looked at some of the curves associated with some of the costs for different flow rates versus the capital cost input for different technologies. And some of the treatment technologies we found, the PFOA may be harder to remove than sulfonates. A longer chain are easier to remove and destroy than some of the shorter chain compounds. Basically, there's limited number of full scale examples. And what is the life cycle cost? We're starting just to put in some of these technologies, but we really don't know what the overall long-term costs associated with those are. When you take a look at the slides, we have operational issues and costs of all the different technologies here, and you can use those as cheat sheets if you're interested in some of these technologies. There's about 25 of those. That's all I had, and I guess the panel and questions.
Yeah, for time, actually, if you want to stay up here, well, I'll ask all the panel members to come back up. So I have some questions prepared, I think for time, since I know I saw there were hands that didn't get to ask the questions maybe during the individual sessions, that I might just ask one, as they are getting settled. And for me, I was thinking of a probably is going to be a terrible analogy, but I have a 5-year-old, so I'm always like thinking of simple terms. To me that like what you all work in is really fascinating and interesting, and but it kind of making an analogy to like the medical world, that we're treating all of the symptoms, and you're doing what the best you can with what you have, but until we treat the cause of what's causing all these symptoms, the kind of process that we have for creating new chemicals and approving new chemicals for use before they're actually tested out, for their impacts and maybe fate in the environment. I wonder if that's come up for you all in any discussions, as with maybe with regulators, with industry, and do you think that's a feasible, from your perspective, something that could actually happen? Do you think we'll ever start to go back to that root cause so that you're not downstream having to deal with all of these issues?
Well, let me suggest a couple of things. If you take a look, for example, the inventory of carpeting that's in the US, we have probably 50 years of inventory that's slowly going to be removed. Carpeting has a lot of PFAS in it, as the stain preventive. It goes into a landfill, and then we're going to have continuation of PFAS leaching out. That's going to have to be managed somehow. So we're doing a good job with, I think, on an overall societal basis for removing PFAS from the products in commercial applications, whether it's from toilet paper or it's cosmetics or pharmaceuticals. But we're still going to have a significant amount of PFAS that's generated from long-term materials that are still in circulation. So I think we have to consider that this is going to be around for quite a long time.
Yeah, my big concern, and Andrew kind of alluded to it, is the replacement chemicals that are coming through that we don't, and maybe Emily can speak to. I feel like in Europe and other places, they screen out these chemicals before they're being commercially produced. And we just don't do that in the US.
Well, I'll tell a brief kind of ironic story about PFAS. And US EPA doesn't like to acknowledge this story, but it's real. Metal finishers in the Midwest throughout the last several decades used to use hexavalent chromium as a finishing touch on their processes. And US EPA said, hey, we've all seen Aaron Brockovich. Hexavalent chromium is very bad once it gets into groundwater. There are very significant health effects associated with hexavalent chromium. We need you to switch to something else. And that something else, is this on?
Yes.
Okay. Was PFAS. And so the irony that in the story behind emerging contaminants from a biology, zoology perspective is, you don't see the effects until later. And the whole concept of an emerging contaminant and educating policymakers on just chemical uses in society and commerce, it's so challenging. You are mitigating the effects years after they've already been in our environment. And the sad thing about PFAS is there's so many chemicals and they're precursors and they transform and they reform, and the science is not sophisticated enough. We haven't spent enough dollars to invest in the investigation of the health effects of these chemicals. And it's just like a dog chasing its tail in some degree of how do you deal with such a pervasive, ubiquitous chemical that we really don't know too much about. Other than that, what Andrew was talking about is that levels are dropping of certain ones, but there are a whole suite of other ones that are thousands that we don't know enough about.
Right, so I have strong feelings about it. I like when I talk about PFAS, I'm like, especially from the paper companies making paper plates. Like I personally wouldn't mind having a soggy plate. Like I think that we're so easily enamored with things that are provided to us by these advances, and no doubt, like PFAS has been sort of a miraculous consumer product. It's it's made things easier to use. But my utopia were like everything's vetted. Now, I know beforehand, strongly, with state transport, risk assessments from cradle to grave, it's very unrealistic because of the number of things that are already out there, but we have like, I think about it, like we have less PFOA and PFOS. We don't know about, the things that have replaced them. We're hoping because they're shorter chain, maybe they're not as big of a toxicity risk, but like dioxin is the same story. Like once we focused on dioxin, there were some very low hanging fruit, municipal waste incinerators and a couple other things. And now if you look at the record through time of dioxin and sediments, it's gone way down. And like Michigan, I think that was the state you were talking about in terms of industrial pretreatment and going back upstream.
Yeah.
They've done an amazing job of bringing down PFAS in biosolids, but the problem is it's like that's one. Like we can't do this like if we do this every 10 years, it would take almost 1 million years to get through that backlog of 100,000 compounds that we don't have all of that information for. But it would be like to focus a little bit more on green chemistry and what might be a balance between having just that right consumer product that doesn't make our hand greasy and something that will break down naturally, or probably polybrominated diphenyl ethers. With the flame retardants, I mean, it kills me. They're in absolutely everything. I mean, I'm sure in certain situations where we're probably more likely to get flame and have that do its work as flame retardant, that's fine, but it's just in absolutely everything at very high concentrations. Car seats, carpets, and we probably don't need that much.
Yeah, and maybe to extend that analogy just a little bit is, so assuming like maybe we can't change that process, how do you, today it's PFAS, tomorrow it could be something different. So how do you kind of take the lessons that you're learning from this PFAS issue and maybe others that you've been dealing with and think about how do we transform our kind of waste recovery and management systems so that they're better prepared maybe for some of these, future emerging contaminants?
How much dollars and
Unlimited budget.
I mean, I think if you think about it in the circular water economy way, it would involve discussions with the manufacturers of these chemicals day one. I feel like another reason why PFAS is such a big issue is because a lot of this stuff wasn't made public for a long time. They knew about the toxicity of it and certain things. I don't know, a better collaboration at the point of new products entry. I don't know.
we're trying to get rid of it. One of our clients is a company called Darnell in Monroe, North Carolina, and they make some of the fiber plates like for Condoba and some of the other, and they have a specification of 140 degrees with no grease transport, and they can only without PFAS, and they use PFAS for that. And they've been struggling with that for over 2 years, and with non-PFAS components, they can only get to maybe 120 degrees with no PFAS transport. So we're struggling with this. There's no potential option for that right now. They can't supply these plates, to all the fast food restaurants. McDonald's and Burger King have stated the goal of no PFAS in any of their wrapping by 2026. I don't know if that's going to happen or not, but that's a goal. But we're struggling with it, and chemistry. These are performance chemicals, and they perform really well.
Yeah.
I mean, that's part of it. But it's a struggle, and we're all dealing with that.
Well, I think if we focus on essential uses, like I don't think that's an essential use, and they should be phasing it out. But there's still a need for it in some cases.
I would agree with Janine. I don't know if you can really regulate your way out of a PFAS problem. I think this is a societal issue, and if you ask anyone on the street about PFAS, they have no idea what you're talking about. We've become so ingrained in this issue. It's just such a fascinating time to be experiencing this, because there will be something that comes next. And when I was talking with Matt, when we were putting kind of our thoughts to this, from a utility perspective, utilities don't like uncertainty, especially in the regulatory context. So much of their budgets go to meeting existing regulations. And that's a huge cost for them because they want to be in compliance. They want to be stewards. They want to protect public health. And so when you disrupt that, with an emerging contaminant, it's hard to plan, it's hard to continue operating with your communications team, talking to your ratepayers, etc. But also, they're already dealing with high costs to meet environmental compliance needs. CSOs and lead from lead service line. They to introduce something entirely new and think of how quickly this is all happening is very challenging for them. So I don't know if there's necessarily a regulatory solution. And I think we should be thinking about how ourselves and our communities can get rid of PFAS in our everyday uses.
You had a question?
Well, I was actually just going to add on to that. So I'm with the Water Research Foundation, and we have done some studies on this exact issue, pre-PFAS even. Actually, I think PFAS was emerging while we were doing the other project. We were looking at ways to address, at the time, we were more concerned about pharmaceuticals and personal care products and endocrine disruptor compounds, et cetera, and how to prevent them from getting into the environment, looking at, triple bottom line, where we get the most bang for our buck in removing those compounds. And we were partnering with European researchers as well as US researchers. And they did talk about the European perspective, and there is a program they have called REACH, and they do hold their chemical companies more accountable. Basically, not only do they have to submit more information prior to registration, but they can be held accountable years down the road if in the future there are impacts that are found. And so it does cause them to do a lot more research prior to their certification. So I do think there are ways. I agree with what you were saying. We're not going to regulate our way out of this issue, but I think we can do more in terms of public education. We can do more in terms of educating our regulators, trying to get advocate for water to have a seat at the table when these things are being discussed that may have some impacts down the road. And then there is more we could be doing in terms of just general source water protection that prevents not just PFAS, but all of these other potential contaminants. One of the other interesting things we learned from that prior project was another European initiative. I think it was only maybe in Switzerland actually, but they were much smaller country, much more money that could be spread around. But they were looking at doing ozone biofiltration at across the board for wastewater treatment, and that would prevent not just PFAS or some of these other things, but any future contaminant du jour. So I think it's fun to kind of brainstorm these things, but in reality, I think probably the best we can do right now is the education outreach and try to do more source water protection. But I'm curious, hearing all that, if you had something else you wanted to add there.
I heard your boss, he said it perfectly one time. It's not the contaminants are not emerging, it's the concern that's emerging,
Yeah.
right? These
Yep.
chemicals have been around forever. I feel like if we had known about it, there had been more transparency with the manufacturing process, we would have been in a totally different place now.
Yeah, we did another project that was specifically looking at alternative mitigation strategies for PFAS. I think Carollo did it for us just last year. And I mean, really, it all boiled down to the same thing. Try to
It's too
treat it, you can do industrial pretreatment, you can try to educate the industry a bit more, but it's hard to hold them accountable.
Janine, you said these chemicals have been around forever. Does that make them forever chemicals?
we know we can destroy them now. But at what cost?
I can ask more questions, but I'd also like to see if there's other
I
audience.
have one related, kind of redirecting us towards phosphorus a bit. So, a lot of treatment plants are managing nutrient regulations and these fear of regulations of PFAS and biosolids. And so one thing that I'm thinking as a researcher is, does it make sense to try to segregate the value of nutrients from the biosolids? Or
Yes.
do we want to aggregate them and combust or pyrolyze. I think, you know, in terms of kind of balancing the benefit of what's embedded in that matrix, because it isn't the majority of organics in this in the country. What forms of treatment and resource recovery do you think make most sense to reduce risk and meet current regulations while looking forward to what could be coming down the pipeline?
I have strong feelings about that too. I've got strong feelings about everything.
It's great, I
But
love
I
it.
actually, I think from the perspective of phosphorus for both manure, actually it's waste manure and biosolids. The idea of extracting some amount, preferentially pulling out phosphorus makes so much sense. And I've actually now worked on a couple projects where there's been a DAF system in place to essentially create after a digester to create a material, a digestate that has a nutrient balance that reflects that of what the crops are taking up. And to me, that's brilliant. But on the other extreme, I just love organic matter based byproducts, manure, whether it's manure, compost, digestate. And I hate to see a rush to pyrolyzing, incinerating, or even subjecting these materials to supercritical water oxidation. Now I know that in some cases, because of the contaminant issue, maybe that's the route you have to go in. But I feel like there's a lot of benefit to soil health from fresh organic matter being added to the soil. And so I feel more strongly about that and trying to clean up in any of these streams what's actually in it, which is like, again, it's sort of a utopian, it's kind of pie in the sky. But that to me is more important than figuring out how to destroy them, because I think it is the case now. At first, when we talked about combustion or pyrolysis, we knew that it wasn't in the ash, but didn't know if it was in the air or condensate or something like that. I think, and you guys probably know better than me, but there are ways out there to treat the air too, to oxidize it in the air. So that's, you can do that, and then you have a material that's really clean, but in terms of returning that to the soil, both in terms of energy use, well, in some cases it requires a lot of excess energy, in some cases not as much, but in terms of like the benefit to soil health, I'd much rather see it go to the soil in the form of organic matter than something that's been combusted. Yeah, yeah,
Mineral.
yeah.
Doug, did you have? Okay.
I mean, along those lines, what's the fate of the fluorine when you do combustion of, let's say, a biosolid?
What type of?
I'm hoping you might know that.
Well, I'm
I'm
asking.
on the far end.
Oh,
Well, maybe Emily.
no, go ahead. Ivan, probably. What do you mean by combustion?
Hydrofluoric
I'm
acid.
talking incineration.
Yeah, combustion.
Yeah. Well, because pyrolysis and gasification often get confused with incineration from a utility perspective, and they don't have the same thermal processes. Go ahead, I'll let Ivan answer and then I'll add 2 cents to it.
Yeah, you get some mineralization of some of the constituents. However, fluorine is such aggressive chemical. It's going to bind with something else. You may get some hydrogen fluoride coming out, which if it hits any moisture, is going to become hydrofluoric acid, and then that's going to be very corrosive and it's problematic. There's a lot of research that's been done. A lot of research needs to be done in the incineration aspect associated with that. For example, the supercritical water oxidation, which has some of the similar characteristics. There was hydrogen fluoride generated, but that can be captured if you, for example, subject that to a limestone solution. You're going to get calcium fluoride generated, and that's pretty stable. So there are some aspects that can minimize some of that fluorine emissions, as well as some of the other constituents.
Just about all combustion systems for biomass, typically have a limestone, stuff is going through a limestone bed, or they're injecting limestone or calcium hydroxide into it. So calcium fluoride's hunky dory.
Yeah, it's pretty stable.
Okay, so I mean so combustion, there doesn't seem to be any downside.
Yeah, there really are, because we don't know what the other constituents are going to be. It may produce, for example, very, very low concentrations, but you still may get some concentrations of some of the PFAS constituents and some of the other compounds. You may not be totally mineralizing everything. So I think there's a lot of concern associated with that. You know, it was banned by military and EPA for quite a number of years. There's some studies in Cohoes, New York, on some incineration that really showed there was other constituents that were coming out. New Jersey had some test runs that showed there was real concern with some of the air emissions. So I think that's problematic. Besides that, if you have 2 or 3 second dwell time at somewhere it's approaching 1100 degrees centigrade, it shows you may get some really, really good reductions. But what about any operational considerations for bringing the temperature up, bringing the temperature down, emergency shutdowns? So there's a lot of questions associated with the operations of those incinerations.
Yeah, I mean, it's big in New England, and we're keeping an eye on it because it's something the operators are comfortable with. It's established technology. It's 3 T's: time, temperature, and turbulence. So they're doing a lot of experimenting with the time, as Ivan mentioned, turbulence and other things to get that PFAS destruction.
Then the one thing I would add, when you think about incineration, the Clean Air Act is a heavily focused, it's heavily permitted. Sewage sludge incinerators, whether you're operating a fluidized bed or a multiple HERP incinerator, they're shuttering because the compliance requirements to continually operate and maintain these systems is getting harder and harder. And then you throw PFAS into it, where you're trying to manipulate maybe the temperature or the time or the turbulence, and you're throwing other operational things awry. And so utilities are faced with a dilemma where they may operate, a sewage sludge incinerator and land apply and landfill. And if any one of these is eliminated to some degree from whatever reason, they're faced with a really crisis situation, as Janine was mentioning, in Maine. And I know from some of our members in Massachusetts, they don't like accepting feedstock from other utilities because you don't know what's in it. Because if they know what's in their product and they test for it and then they burn it, they have a guarantee that they're going to be in compliance, as long as it's operating and functioning as normal. So there's a competitive business here of, I'm not going to share my feedstocks with, I'm not going to open it to other folks because I don't know what's in it. And I could be out of compliance because of it. So the combustion practicalities for a utility right now, I think we're wary to even discuss that. We're most focused on, we have to maintain these 3 pillars, because if any one of them goes away, we're in a real problem. And so we've got to try to figure out the solution to land application because of the nutrient benefits and the costly alternatives, rather than think too far ahead to incineration and its downsides. I don't even think they're there yet, and I don't even know if there's really a EPA method for testing air emissions off stacks. So that's years away, I think, in the game of biosolids advocacy. Is let's just make sure we can maintain at least the land application for the time being.
Yeah, there are some methods, OTM 45 and OTM 50, for air emissions, but they're very, very expensive. They're very difficult to run correctly. It's just a lot of issues associated with it. I would stay away from incineration if it were me.
We've got time for one last question, and only one of you can answer. So this is it.
Hi. I'm interested in biological solutions to technological problems. So, Andrew, you mentioned at the end of your talk that PFOAs and PFOSs were not shown to have much, there was not much efficacy in conventional composting to break those down.
Yes.
What about unconventional composting methods, anaerobic composting methods?
Well, so what we have seen is data from digesting
Right.
material in an anaerobic environment, and essentially what I've seen to date, and I work a lot with Dr. Linda Lee from Purdue, who's done a lot of PFAS work. And this is essentially what she told me, but it seems like it's what I've seen anecdotally as well, that anaerobic digestion is somewhere in between, like it is in so many things, like that raw material and composting. So there is some transformation that occurs of precursors to those terminal products, but it's not as favorable an environment as it is in an aerobic, a composting environment. So it doesn't seem to break them down. We still have to seem to have this transformation from those precursors to the terminal products. So it's unlikely, at least with those larger compounds, 8 carbon and higher, from what I've seen, that anaerobic digestion would somehow be better, like have some efficacy in breaking them down. But there may be some other.
A combination of that and biochar, perhaps.
Yeah, possibly. It's hard to say. I think that it seems like to make sense to look for a biological solution, but I haven't yet seen one, and it doesn't mean it won't work. And it's the same with fungi. There are reports every once in a while that there's certain sort of fungi that might break them down. I think it will be a long time before we'll see that done effectively on a field scale. But it's totally worth looking into.
We gotta cut it there, folks.
Okay.
I'd say keep the conversation going with beers or tequila. Wine from here.